Welcome back. Welcome back to our PV solar system design series. Today, we are going to start part 2. In the previous part, we introduced PV solar system. We introduced what's renewable energy, what's renewable sources. We spent almost less than an hour to talk about the PV solar systems. Today, we are going to start the detailed design of our series. This detailed design will go through multiple number of lectures. During today's presentation, we are going to focus on the grid connected system. We are going to talk what's a PV solar panels, what's a PV panels data, what sort of data I need from the panels to complete my design. I need the sun path. It's very important for me. This sun path will stay with us for the rest of our series lectures. I need the system required area. I'm doing for a residential property, for example, or for a commercial. I need to make sure that I have the required area for the design. The PV system layout design. For example, I have 2,000 panels. I have 20 panels. How do I put them? Do I put all of them in series, all of them in parallel? That's the PV system layout design. And then I have an inverter. I chose an inverter, grid connected inverter, because I'm working now on a grid connected system. And I have, for example, 20 panels. How do I complete the connections? Then system commissioning requirements is included, maintenance requirement, and high level cost. All this will be captured during today's presentations. All right, guys, let's start. Photovoltaic panels. The panel that we see, it's made of cells. The most common cell materials, this is a cell, thin film, monocrystalline, and polycrystalline. These are the most common used currently. Previously, they were monocrystalline, polycrystalline. Now the thin film start gaining some momentum. Now, PV cells, the PV cells are connected in series and parallel to form the panels. And depending on the number of series connected and the parallel connected will determine the panel data that's required for my design. Cell voltage for maximum power output is around 0.5 to 0.6 volt per cell. And you will see now when we go through our presentation. The cell current, for a maximum power, the solar cell, uses the sun radiation as an input. So based on the sun radiations, I will have my solar cell current. And you will see for the voltage, it's almost very close to a same value. Now I have a poly solar cell, PV cell, and I have mono solar cell. I want you to pay attention. Look guys, for a poly, I have my current under 1000 watt per square meters. This is a square meters, guys. This is a square meter. For this system, I have my current is just under 9 amps. I have my voltages. It's basically for a maximum. See the maximum? It's just between 0.5 0.6. For a mono, as you can see, the current is higher for the same sun radiations. And as you can see, the sun radiation changes, the current will change. But as you can see, the voltage is very close. See the voltage very close. That's why mono, it's high efficient. And we explained in a past lecture what's mono crystalline and what's a polar crystalline. This is, for example, look at this. See the difference? The voltage vary just above 0.5, maybe 0.55. That's why for a maximum power output, irrespective of the radiations, the voltage changes slightly, maybe 0.54 to 0.56. However, for the current changes big time, depending on the radiations, between just under 5 to maybe 9.6 amps, depending on the radiations. Solar cells, when they are connected into series, as you can see, I had the solar cell connected, see? I connect this into series. I have 1, 2, 3, 4, 5, 6, 7, 8. For example, let's say, to make my calculation easy, 0.5, then 0.5, 0.5. I keep at it. At the end, I will end up with a voltage. N is the number of panels in series. This is N, is the number of cells connected into series, multiplied by 0.5 or 0.55 or 0.6, whichever value you use. So that's how we determine the voltage of a solar panels. If, for example, in my solar panels I have 36 or 72 cells connected in series, I do 36 multiplied by the optimum voltage of the cell. And that's how I determine these numbers. Now, I go back. I need to define the panels. The solar panel data that I'm interested for my design, I'm interested into short circuit current, into open circuit voltage, MPPT, maximum power point voltage, and for the maximum power point current. If I go back to what I showed you in here, this represents my short circuit current, this represents my open circuit voltage, and the MPPT is located at a maximum. So you know that P it's equal to VI. So multiply the voltage with the voltage, this P will be represented like this, somewhere like this. And this is where my P maximum power point, which is located at this current, if this is the case, located at this current, and located at this voltage. So this system in here, I call it IMPP, and this now for me is VMPP. Is that clear, guys? Let's pause this for a second. All right, guys? Is that clear? So that's what determines for me the MPPT current and my maximum voltage for maximum power output. So now if I go back to where I was, I'm interested in the short circuit current. The short circuit current for my panel depend how many cells are in parallel. If all of them are in parallel, that means the short circuit current for my panel will be the same as my short circuit current for the cell. Open circuit voltage. Are all these cells in the panel are in series? So what I do is I will add the open circuit voltage per cell and multiply it by the number of panels in series. MPPT, maximum power point voltage, maximum power point current. It's based on the circuit that we just saw before. Is that clear? No. Currently, available in the market, I have up to maybe 410, 420 watt rated power per panel. So this rated power, if for example I go ahead and I obtain a panel, any panel, LG, Canadian Solar, any panel available in the market. If I obtain a rated panel, for example, 250 watt or 410, this rated power is at when I have a sun radiation of 1,000 watt per square meter. 1,000 watt per square meter reaching my solar cell within the panel. For example, for a Canadian solar 350 watt, can you see this? Look. When I have 1,000 watt per square meters, I have my current is about 9.8 maybe, 9.7. Can you see the voltages? It's almost very close to each other. But the current will vary from less than 2 amp to almost 10. So there's almost 8 amps variance. However, the voltage, look, the voltage vary between 47 to 43. Is that clear, guys? No. What will happen is, this is my radiations. What I need the current that it's at a 90 degree on the panel. At a 90 degree on the panel, I need this to be 1,000 watt per square meters. As you can see, depending on how I tilt my angle and how I orient my angle, this will change. This will change. So for example, if this now 1,000, the sun is giving me 1,000, based on my angle tilt, based on this angle, this no longer 1,000, this no longer 1,000. Could be 900, could be 950, could be 800. Can you see? And this, what will happen to my system if, for example, it's not 1,000 now, drop to 800. See the 800? So now, can you see I dropped my current almost 1.5 amp? I lost from my current. That's why the sun orientation, sun path, and my tilt of the panel is very important. Today we are going to check the sun path. And this is where the MPP, the maximum power, depending on as you can see, the voltage is the same. What changes is the current that will drive the power to go down. And as you can see, it's almost the same voltage. See, it's almost the same. If you draw a line, there's only a little bit changes in voltage. Now, the sun path. I need to have panels installed in series and parallel to meet the required load. So this is an example for a panel connected in series. When I have the panels connected in series, I call them string. So I have one string, I could have 10 panels, 20 panels, 5 panels on one string. When I add multiple strings together, I call them an array, PV array. This is the definition you should get used to. You should get yourself familiar with, because it's very used. I have a string contains, for example, n number of panels. I have 3 strings in parallel to form my PV array. Now, today we are designing a grid connected system. From our last lecture, this is my grid connected system. See, I connect to the grid. I have a solar panels going to my inverter, and then from my inverter give to the house or to the grid. As we said before, for this system to work, it requires a 24/7 electricity from the grid. Before we go ahead into the design of the connected system, grid connected system, it's very important for me to check the local utility policies. Allowable system size connection. The utility refer to the AC power. For example, some utility will allow you to connect 5 kilowatt or 8 kilowatt single phase. Will allow you maybe to connect 10 kilowatt 3-phase system. Then the type of allowable system size connection. Is that 3-phase or a single phase required? Additional requirement. They might have some sort of additional requirement. So it's very important to check the utility in your country or your area before you go ahead. Number two is, I need to connect number of solar panels. It's very important for me, it's very vital to have the available area. What do I mean by suitable area? As we saw from the cell and the panel, I need the sun radiations. To maximize the sun radiation, I need to have a suitable area with suitable sun exposure to my panels for me to derive the maximum power of my system. Therefore, the available suitable area is governed by the sun orientations and exposure at the desired location. This is taken from this source, these couple of slides. I gave you an example, Lebanon, in the Middle East, to show you how does the sun changes throughout the year. For example, in January, midday, the angle to ground is, as you can see, it's very 34 degree. However, this is at midday. At 10 a.m., it's at 22 degrees. And then changes, the sun in the summer goes up, in winter goes down. So the sun orientation changes, and I want you to pay one attention to this. This, for example, southeast, this is the east, and this goes back to northwest. As you can see, the east, it's only happened, the true east for solar, it changes throughout the season. Therefore, it's very important for me to determine which season I am designing for. Am I designing for winter, spring, summer, autumn? Because based on my season, the sun path changes. Because the sun, as you can see, changes throughout the season and the day. Look now, for example, in 78 degrees for winter, for summer. In winter was 34 degrees. This table was done based on previous research conducted. It gives you 10 a.m., 12 p.m., 3 p.m. The orientation, what I mean by azimuth angle, is the angle goes from here all the way down to here. This is the azimuth angle. And the tilt degree, the optimum tilt degree. So, for me, if I'm designing, for example, for the summer, as you can see for the summer, midday summer, that's when I have the strongest radiations, will be about maybe 10 to 20 degrees orientations. For April, 30 degrees. For October, the tilt is 1st of October, 39 degrees. The tilt. So for the summer, I can conclude based on this table, for the summer, in the Middle East, I should orient it toward the south, facing south at an angle tilt maybe 15 to 20 degrees. For the summer, that will be suitable for maybe June, July, August, and September, mid-September. For the Middle East, the sun radiation is the strongest during the summer. That's exactly what we said. The other angle between 180 to 210, so facing toward the south, a little bit the southwest, and must be facing north. That's a project we installed in Lebanon, and as you can see, you have to have a tilt angle and facing toward your desirable output. Now, as you can see, I need multiple panels to be installed. For example, in here I had 12 panels installed. I need to look at the area. I need an area, as you can see, I need an occupied area and a clear area. Not all houses, not all places have the sufficient required area. So first I need to determine the area required for my system. Okay? First of all, I need to determine the maximum allowable AC power that the utility allows me. For example, in this case, the utility allows you to install this. I need to go back to my inverter. I choose an inverter. For example, I choose an inverter that has that much power. I go back to the inverter. I need to check my inverter. What's the maximum DC power at the inverter allowed? Because the panels generate direct current, DC current. I need to be able to size the number of my PV panels in the area based on the required DC power, not the AC. AC is governed by the utility. Then I choose a PV panel. Every PV panel, as we saw, has a rated power. Could be 200, 250 watt, 300, 360 watt, 400, 410 watt, depending on your choosing panel. Then I have an area. Every panel has an area. And then, like we said, you have to tilt. You have to design at a tilt angle. At the end, I use this equation to determine the area required for my system. Now, guys, I want to get rid of this cosine. I want to design a conservative system. This system, cosine 30 or cosine 20 or cosine, it's like 0.86, 0.9. So I want to allow for this 10% margin, so I can design using only the area, using only this equations. I don't have to worry too much about the cosine alpha, but if you want to be more accurate, we can design a cosine alpha as well. Now, let's take an example. I want to design my system, I want to design a system to install 5 kilowatt grid connected using ABB React 2 owner inverter. I want to use a Canadian solar rated at 250 watt. So what I've done is I went and I want to purchase ABB Uno grid connected inverter, and I want to purchase Canadian solar 250 watt panel. From the ABB data sheet, I see that, hold on a second, the Uno can accept DC power is 6,000 watt on a DC power and gives me an output power of 5,000 watt. So I need to design my system to optimize my operating system. I need to design a 6,000 watt DC system. I go back and get my panels, my data sheet for the panels, the 250 from the Canadian solar. Look, this is the dimension, this is the area. 1.638 multiplied by 982 millimeters will give me 1.6 square meters per panel. If I go ahead and I do this, the total area, I need to have 6,000 divided by 250 each, multiplied by 1.6, it's equal to 38.4 square meters. So for my system, I need to have the project required 38.4 square meters of area that will allow me to tilt. For example, if it's in Lebanon, I need to tilt facing south, tilt it maybe by 20 to 25 degrees. If I'm designing for the summer, tilt depending on your season. You can choose from the table. Now, PV layout. The PV layout, when I have the layout, we spoke, is it going to be all in parallel, all in series, the panels? I need to determine the layout of my panel installation design. It's governed by the panel data, as we spoke, maximum power, as we spoke, voltage for maximum power, current for maximum power, open circuit and short circuit, and also by the inverter data. Every inverter you have, it's governed by maximum voltage, by an optimum voltage, by number of connections, by startup voltage, cutoff voltage, by a linear derating system. So I need to check. I cannot, if I go ahead and I put on this inverter ABB, if I put a 1,000 volt open circuit, I could damage it. I need to obey with the inverter data. Let's take a moment to digest this information. So as we said, I need to be very, very vigilant, very careful when I connect the system in series and parallel. Also, every single inverter has a maximum current capacity. Maximum current capacity. See? Maximum DC input current, DC max, IMPPT max, and the voltages. So now I chose a inverter, then I chose a panels. I need to design my layout. Great. I go back, check my panels. Hold on a second. My panels has two inputs. When I say two independent MPPT, that means I can have two different connections to my panels, to my inverter. So this inverter is capable of taking two different panels array. And look, each one of them will have 3,000. See this 3,000? Each MPPT can have maximum of 3,000 watt. Maximum of 3,000 watt input on a DC side. So based on, I'm choosing, guys, I'm using 250 watt Canadian solar. So therefore, maximum of 12 panels can be installed on each MPPT. 12 panels. As you can see, great. The total system can take 24 panels. Every MPPT will take 12 panels. Now, do I connect these 12 panels in series, in parallel? Let's check. What I do is, I need to verify this. The number of panels in series must obey these two. So I always take the lowest. This value, V inverter max, is 575. This is 390. In my case, great, perfect. I can choose 12 panels. 12 panels will work perfect for me. See, I can put 12 panels work perfect for me. I can put 13 if you want, because this system will give you 12.9. Is that clear now how I determine the number of panels in series and parallel? Guys, this can take 15, but if I take 15, I go beyond this. I might go into the derating system. I might go into this, maybe, I don't know. As long as it's below, so I can reach up to 15 panels on this system, but 12 panels will give me optimum. 13 panels also could give me an optimum as well. So 12 to 13 panels will give me an optimum design in series. However, remember I maximum can put 24, so I divide them 12 and 12, and I just verified that 12 panels doesn't exceed the maximum VOC and doesn't exceed the 390. Like I said, in here it is acceptable. You can put 13, that's fine. Tomorrow when you become very experienced in this, you will see that the panel, if it's 250, it's a very rare to give you more than 220 or 230. So we can adjust this. But now, for you as a start, let's stick to these equations. Anyway, they already allowed for an extra 1,000 watts from 5,000 to 6,000 to compensate for this much. Okay. Now the layout. I have an ABB reactor. I have 5 kilowatt AC, this is comply with the utility. This is perfect for the utility. 6 kilovolt DC, perfect. I have 2 MPPT. What's our my 2 MPPT? I have MPPT1, MPPT2. And I said to you, each MPPT can take an input. Based on the design that we just did, 12 panels can be connected or will be connected in series to each MPPT. So what I do is I get it like this. So I put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 in series. And then I connect to MPPT the second one. So now I have the total connection is 24 panels to this one, which is the 6 kilowatt. Like I said to you, tomorrow when you become more experienced into this, you will see that even if I put not 24, even if I put 26, if I add 1 in here, it shouldn't matter for me. Because the power of this one will never reach 100%. 250, the 250 only will happen if you go to the data sheet of the panels when it's at 25 degrees, 1,000 watt per square meter at the panel. When the temperature increases, because it's made of material, conductive material, the temperature increases, the resistance increases, the efficiency of the panel decreases, which means you will not get to 50. If you have, for example, if you have 1000 watt square meter hitting the panel at 35 degrees, you still don't get the 250 watt output of this panel. But now we're doing the design. This is a good design system. After we design the connections, now I designed my connections. I need to go back and commission it. Now I finished. I installed it, I did the installation, I put the infrastructure, I did everything. I need to commission my system. How do I commission my system? This is one of the most important elements, commissioning steps. Guys, every single inverter has some different requirement. However, this outline the standard requirement that I strongly recommend you guys to follow. Because if you follow this one, at least you cover the majority of the safety requirement for your system. Ensure all required electrical protection are installed. We will designate a separate lecture at the end to do the single line diagram for all the protection required on the AC and the DC. The aim of this lecture is to give you an idea about the sun orientation, which is now this sun orientation will stick with us for the remaining of our lectures. How to connect in series and parallel, what will change, how to read the data sheet of an inverter, and what element of the inverter I'm interested in, and what element of the inverter is related to each element of your solar panel. Ensure the inverter is mounted as per the manufacturer manual. It's very important to make sure that it's being installed as per the manufacturer, the way it's being mounted, especially for separations, filled, all the stuff has to be compliant. Double check the cable connection and coloring. It's very important. So, for example, in a lot of countries, yellow-green is for ground, for earth. So make sure that all this stuff is done. Make sure that cable sizing, cable connection, is it all correct? Double check. Use your multimeter, use your machine. Make sure all these connectors are in off position. All your disconnectors, all the circuit breakers are in off position when you do that pre-check. When I'm doing this check, it's very important to have open. Test the voltage terminal at the PV panel connection. Now I have the PV panel. Don't I have a 12 and a 12? I will take this. I have a positive negative connected to MPPT1. I have a positive negative. For example, this is my MPPT. Different one. I have two wires coming to it. Positive, negative. I get my multimeter. Make sure the multimeter is rated for this voltage you're expecting, because now you know I'm expecting they're all in series. So I'm expecting under open circuit, I'm expecting 12 times 37, as we saw before. 12 multiplied by 37 is a V open circuit for this type of panel. I measure it. Am I getting similar? Doesn't have to be exactly the same. Am I getting close to it? Check the polarity. This is positive, negative. So I check the polarity. Remember, it's open. Now, this is my panel. This is my PV panel. I have this disconnector is open, so I'm checking out these two terminals. Negative, positive. Is that negative? Is that positive? Is the voltage correct? I complete this check to verify the voltage and to check the voltage polarity. It's very important before you turn it on. Now, a lot of inverters has already this polarity check internally. But let's do it ourselves in case your inverter don't have this privilege. Then, check grid terminal voltage. So for example, what I do is now I have, this is my grid. I have the grid coming up. Is it single phase or is it 3-phase? If it's single phase, I have now, this is my inverter. I have an open, everything is open. I test this one. This is line to neutral. I check, for example, my system inverter, is it to 30 volt? I check, is it to 30 volt? 50 or a 60 hertz. I need to check. If it's a 3-phase, I'll check line to line. And the frequency. Make sure the grid terminal voltage match the inverter data. You don't want to connect 230 volt to an inverter of 120 volt. Make sure you connect the right voltage to the right inverter. Log into the inverter interface. For example, a lot of inverters, I want to talk about, let's say ABB, Schneider, SMA, all of them, has an interface portal. You log into it, you do all the setting as per the manual. I'll establish the connection between the inverter and the grid. Check the inverter reading. So first, before I close the DC end, I will close the AC. So now I have the grid connect the inverter. I have the signal coming to the inverter. Beautiful. Now I check my inverter. After I did all the setting, I check my inverter. The inverter should tell you, hey, there's a grid connected, everything is good, no fault indicated, nothing. Then I go ahead and I close the link between my PV panels, the DC, and my inverter. You have to take note of this. Some inverters has a special startup. Please check the manual. Some of the inverters has a lot of different minor changes, but this step should be the minimum guidelines for you. And also, most of the inverters has an internal delay. Before they finally connect to the grid, they do an internal check. If there's no matching, if there's no sync check, it will not connect. It will give you an error. I hope the commissioning stages is clear. Maintenance. Usually, a grid-connected system has a very, very low maintenance. However, based on my personal experience in this domain, I recommend the following step. And you guys, depending where you live, you should check for cleaning maintenance. It's very important, guys. So I do this. Guys, sometimes you install a system, you will screw all your bolts. Because you have wind, you have a vibration, depending where you put it, some of them, it will lose. That's why the washer is very important to be installed. But for any reason, sometimes you forgot something, so please go back and do a check. At least if after 3 months of installation, because give it some time to rest. Please, it's very important to do this. Or after a windy day. At least for the first year, let the whole cycle to go through. Because that means you will have a winter, summer, spring, autumn, that means all the wind, all the heavy sun, everything. If there's any adjustment, it can be done. It's very important, guys. I strongly recommend you to go do these steps. Now, this is one of the most important. Check the panels for dust and soil residue. Heavy wind, depending on your surrounding, do you live next to a desert, next to an open area, next to a very big farming where there's a flowers residue. If you have any residue stuck on top of your panels, it will reduce its output. Because now when the sun comes in, when the sun comes into your panel, it doesn't reach the solar cell, it will get reflected by this residue. It's like I put a cover, a shade area. That's why it's very, very important to check for this one. And then perform cleaning as required. Perform cleaning as required. Check the electrical connections. I recommend you guys after a while, because there's a lot of wind, your cable check. Number one, is my cable now solidly connected? Still all the cable ties properly done? Is there any loose connection? I check all the stuff in case I forgot about it, especially during the first year, during the first storm. Financial assessment. Financial assessment is what do I do for my financial assessment? I give you an example. I have an inverter of 5 kilowatt, cost 1,000 for example. I have a 24 panels. Cost of the panel is all the panels 2,500. I have a structure that costs 5,500. I have a labor installation of 600. So the investment budget will be, I add all of them together, I end up with 3,600. This is a rough estimate. Okay? Now, I need the system installation. The system installation is in Lebanon. I run a quick simulation, which is one of the lectures I will teach you how to use one of the simulation tools, software, how to can advance use it for everything. We have a generation of 10,069 kilowatt. our per year. This is the yearly generation. So my revenue, I assume in Lebanon, there's very rare any maintenance. Sometimes the individual person for the 12 panels, they can clean it maybe once every 6 months, once every year. And because of the rain, there's no dust, a lot of dust, there's no sand. So cost per kilowatt hour is 11 cents. I'm saying the cost per kilowatt hour is 11 cents. Guys, if you are using diesel, generator to support your electricity, this could reach 100 cents. Just giving you an idea, 80 cents for the diesel per kilowatt hour. So the revenue per year is $1,107 per year. So therefore, based on this, my system required just over 3 years to return on investment, to return my invested amount. Now, the panels has a working life for 20 to 25 years. Some panels start derating after 15 years. Can you see the numbers? 3.5 years to return on investment. I have a revenue, a warranty, or an operation life for the panels for after 15 years start derating up to 25 years. Great. What else I have? The inverter. Some inverters has warranty for 2 years, 5 years, 10 years. But can you check the inverter cost? The inverter cost is, for example, $1,000. It's not the entire system cost. So even if you have to replace it after 5 years. Guys, based on my experience, standard inverter, if you put it, you don't overload it from a DC or an AC perspective. You protect it from lightning. You do all the proper protection for it and all the proper installations. It will last between 5 to 10 years, the inverter. What else you have? That's it. The infrastructure that you installed could last for a long, long time. And that's it for this lecture. So what we've done this lecture, I showed you the detailed design for a system, for a grid-connected system, for a residential property. I showed you the required area. I showed you the tilt, the determination of the tilt angle, and the orientations. We showed you how to connect in parallel, in series, based on the inverter, the chosen inverter data sheet, and the minimum commissioning requirement, and then the minimum maintenance requirement based on my personal recommendations, and then some financial aspect. How do I do my financial cost analysis? I hope that was beneficial for you. Guys, until we see you during our next lecture, please stay safe, and I really hope you enjoy this series. Thank you very much.